I'm more of a man when I grow up.
Hey, Christine. Hey, Christine. She's texting. Good. You don't see it yet?
Over here.
Q&A?
Actually, so let's mute yourself right now.
Ha! Oh.
Hello, everybody that's remote. I got echo here.
Hello, John.
I'm just going to kill myself here. Okay, so you're hang up. So we have. But we're just sorting through the getting the projector working. Nidhi, I wouldn't. Hey.
The TWed talk.
Yes, right here.
Sure.
Yeah, have a seat till we have to figure it out then. or you just have to look on with me. It's
Everyone's fine.
we're getting to a weird part of the term where people are very busy and they're. Nidhi, let's just go with it.
Okay.
Yep. Into our, do this Google Hangouts on air.
Oh, okay.
And we have one is the camera, the other is the screen share, so we can anybody watching via the YouTube feed. So let's get started. It's plausible start time, and we'll. And what's your name?
Spencer.
Yes, of course, right. All right. So I think everybody can hear me out there in remote TWed land. Yeah. So thank you for joining us. Those of you who are joining us, you actually outnumber us online tonight, which is great that we're exploring new territory with TWed tonight. And so we're very thankful to have Nidhi Rastogi here tonight to talk about work that will be hopefully will be your thesis work, which is very exciting to hear this. And just a reminder to those in YouTube land and Google Hangouts land that next week is our lightning talks. Do you know about lightning talks?
No.
Are you on the TWed distribution list?
I am.
I mean, so you do get those. So
Yeah.
because I think it certainly can apply to you. I'll explain it a little bit later. So.
And there's pizza, by the way.
And yeah, help yourself to pizza over there.
Oh, sure.
Yeah, absolutely. So Nidhi, why don't you get started? And those of you on the remote, please feel free to get my attention via either the chat, or you could actually speak up. Also, I'll have the sound on. So let's hit it.
Okay. Good evening, everyone. Thank you for joining me for my first talk. Like John said, may very well become my thesis topic. So, exploring graph centralities for detecting anomalies in networks. That's a pretty long topic, but I hope to be able to navigate you through each of these terms and help you understand what it really means, see the big picture, and why did I pick this up as a possible topic. So the research objective behind my work is I wanted to explore anomalies in networks. Networks could be of any size. Right now I haven't really explored what would be the size of networks, whether they'll be homogeneous, heterogeneous, nodes. Nodes basically means anything that is connected to the network. It could be a server, it could be laptops, handheld devices, routers, gateways. It could be any of those. So all of that comprises of networks. Anomalies basically are outliers or unaccepted patterns or behaviors that, as a network security person, one would like to learn more and more about. So instead of saying that I'd like to explore or I'd like to search for network attacks, I'm kind of focusing on identifying anomalies in networks, because that seems to be a more appropriate approach, and I'll explain you in the coming slides why I say that. The research focus is on strengthening system security awareness. System security awareness means being aware of where your system means a network in my research. Being aware of where your system stands in terms of security. And the more aware the network professionals are, the security professionals are of their of the status of security, the more prepared they are in deploying the right tools and really knowing where to deploy them for maximum effect. So what kind of system? Like I said, it could be distributed, homogeneous, and connected network, or it could be any kind of futuristic network. I wouldn't like to narrow it down so soon, so we'll see how that goes. So the need for this research is obviously, this is just to bring people up to speed with the kind of attacks that have been happening. Anthem Breach, JP Morgan, Stanley, Sony Pictures, Staples, they were all attacked in the past 4 months, and we are still in May 2015. And massive attacks, millions and millions of data sets have been stolen from their systems. And unfortunately, this just continues to happen. The numbers keep rising, and the existing tools to protect information, to protect people's identity, all of that hasn't been, I wouldn't say they have been unsuccessful, but they haven't matched up to the kind of attacks that we are seeing these days. So the need of the hour really is not just play catch up, but to timely detect an intrusion or a threat. And for that, my approach is to identify anomalies and then categorize them as threats or intrusion or maybe just a random behavior. So is everybody clear on research objective, or somebody found it too fuzzy? Or?
I think you're fine.
Okay. Okay, common approaches used. These are basically, I would like to go into more depth with these, but maybe at a later time when I'm defending my thesis, because that's when literature study will be done more extensively. So I just wanted to give you a sense of the common approaches that are being used these days or have been used in the past, and you still will be seeing them unless people actually come up with novel ideas, and they are deployed by companies on a commercial scale. So popular anomaly detection techniques, basically machine learning statistics. People don't really understand what they mean, except like generic term machine learning. Techniques are easy to identify anomalous behavior or to basically help detect threats. And same with statistics, where the assumption is that the normal data instances happen in high probability regions. So like in this graph, this is a Gaussian curve. Very easy, and people must have seen it at some point in their academic career. So the center, so what statistical approaches, what they usually rely on is that what is normal happens to be in high probability regions like the center and the ones in between its immediate left and right, and anomalies happen in the far extremes. However, be it supervised or unsupervised subsets, but what they fail to understand is, or even consider, that sometimes extremes are basically normal behavior. You expect certain activities in the network or users to be of that kind, to be sparse, to be little. In those cases, such an assumption wouldn't apply. So statistics and machine learning, the problem that I've seen and I've understood with these techniques is that they kind of rely on a prior understanding of what is to be expected. So that kind of sets the expectation that what you want to see in your network and what you do not expect to see. So what is not expected automatically becomes an anomaly and likely a threat to the network or to the users. So unfortunately, that a priori understanding of anomalous behavior cannot be the guiding path anymore, because the meaning of anomaly changes with the application, with what the intruder is thinking, what they want to exploit. So that changes with time, and unfortunately, because it's very difficult and hard to change how your network behavior, how to detect network behavior in a normal pattern or in an abnormal pattern. Changing that also takes time, because that's like an altogether, you need to replace the technology with something new, or with new definitions or new personnel who have better ideas to identify attacks and threats. So what I'm trying to say through the previous slide is that the main problem does not necessarily lie in the ability to detect an anomalous occurrence, because that has been the practice so far. What I'm proposing is that, and I think I missed one point here, and I kind of even left out that point in any of the slides. The other problem that we are seeing these days is that there is so much data to be mined over here. There's so much data to be mined that it's really hard to apply machine learning or statistics or just any such detection technique, because by the time even the smartest and the best computing technologies are able to navigate through the entire data set, the attack has probably already taken place, or the intruder is somewhere else, maybe at a different level that you haven't really gotten to the point of extracting that data. So again, it again comes back to the security personnel playing catch up.
So just to sort of sum up the point of the existing techniques, for each technique is sort of hampered by the very nature of those techniques, that they rely in order to accomplish the learning, they rely on previous data to learn from, in order to detect a pattern,
right.
in order
Yes.
statistics. It's quite typical, even with the widespread, that what normal statistics would categorize as an anomaly is not necessarily an anomaly.
Yes.
It's statistically sparse,
yes.
but still
yes.
perhaps valid.
Right.
And data mining is kind of in the same situation as machine learning. It's basically the same issue, that it requires a certain amount of data in a certain amount of time
Yes.
to be responsive.
Yes.
And what you're saying is, in this context of a rapidly changing environment,
Absolutely.
it's you're, as you said, you're constantly playing
Yes.
catch up, which
Yes.
is why where we are today.
Exactly.
All right, cool.
Exactly.
All right.
So yeah, but even with unsupervised, where there is no a priori understanding, there is still an understanding in the algorithms that are being used, that what the behavior of the anomaly should be. Either it needs to be in the center of the Gaussian curve, or should be in the extremes. So that is preset, So again, changing that also takes quite an understanding of what you're looking for. Again, changing would mean that you're setting your algorithms to expect certain behavior. So yeah, so these are the two problems that I think are the ones which are hampering or coming in the way of identifying more and more attacks, which is a inability to have a prior understanding of all types of attacks, number one, and number two is so much data that you can't really mine it in real time or even close to real time. And for security, that is very important. For security, I'm not saying you just need to be able to catch instantly or immediately, but fast enough to be able to control or contain the effect of the attack. So again, like I said here, the problem doesn't necessarily lie just in the ability to detect an anomalous occurrence, but it also lies in correctly. So the approach that I'm taking here is in large networks, there's so many nodes which at a given time, well under an attack. it is impossible to have intrusion detection systems of firewalls or even antiviruses of all of them, or even expect them to behave in a way that there's an alarm every time there's an attack. So the issues with network system collecting enormous data, like here, logs, intrusion detection systems, antiviruses, is that they cannot talk to each other in real time and inform each other that this is what I'm going through. This is the anomalous behavior that I'm seeing. Anomalous behavior is the terminology that I'm using. This is the threat that a certain node is seeing, or this is a kind of attack that they are experiencing at a given time. They're unable to talk to each other, which means that they're unable to make each other aware of what the other one may expect soon enough. So, which also means that they are not able to share threat notifications to nodes close enough or even far enough. So, again, it becomes difficult to contain the attack. And thirdly, the collective analysis is either left to the individual, who needs to have a highly sophisticated visualization method to be able to see what is happening at each end of the network, which means that those nodes need to be informing the visualizing interface real time or really, really fast. And
But there really is no such thing
needs
as
to be done like really quickly. And they need to be able to connect the dots. That okay, there's certain kind of attack happening or certain kind of anomalous behavior detected in this node and another kind of anomalous behavior detected in that node. Does it mean that I'm under a certain kind of attack? So how do we do that? Because a lot is left to individuals and monitoring systems. Who are monitoring systems. So the main idea is, and that's what I thought coming from a security and a network background, is that if you're able to, if you're focusing only on, okay, I want to identify attacks, I want to catch threats, then you won't be, so the security researcher will be focusing very, very narrowly on only the attacks that they are aware of. So simplifying the task of monitoring system, that is what my main idea is. That bringing down the understanding of how nodes interact and operate in a network, and just from looking at it from a theoretical perspective, looking at it like a graph, and treating each node like a vortex, and the communication channel between them like an edge. Is it possible to use graph analytics on networks, keeping security application in perspective? So there are concepts in graph theory called centrality, which means identifying important nodes. And there are various ways of doing that, which I'll cover in the given slides. So is it possible to identify special or important nodes with a certain perspective in mind, or with certain kind of information gathering purpose in mind, and identify those nodes and just focus on those nodes to identify anomalous behavior, instead of hoping to get all the data and then analyzing that data collected from all the nodes, and then hoping to catch a threat in time, basically early enough. So the other focus is to cut back on data, which obviously will happen if you're focusing on fewer nodes compared to all the nodes, and analyze that, hence reducing time, which is critical, especially for security of networks. So this is what my main idea is. This is what I would like to accomplish towards the end of my research. That So this is what my research is able to basically accomplish. The motivation behind using node centralities. Node centralities, by which I mean that specific nodes which are central to a network, which are so important that just studying them or analyzing data passing through them will be enough to analyze any information. Information here, to me, means anomalous activity. Because the problem lies, again, with the concept that not every node is capable of detecting all anomalies. So why focus? Why even gather information from those nodes, which will pretty much be noise? And secondly, there shouldn't be an expectation to find attack vectors appearing at every node, which means that if an attack is happening in 5 nodes, why should I be gathering information from out of a network of 50 nodes? There is no need to capture information from the rest of the 45 nodes. So, and the third motivation is security monitoring should be adaptive and contextual. If I am looking for 10 particular kind of attributes, or what do I say, 10 particular kind of I'm basically monitoring 10 types of activities in a node of 50 nodes. Those 10 would give me a different picture compared to a set of another 10 say, attributes or basically vectors that I'm looking at. So that needs to change depending on the kind of information that I'm looking for in those nodes. It should not necessarily be coming from all the nodes. So security monitoring, when I say adaptive and contextual, it means that the story should be, or the attack that the network is, the network basically, what I'm trying to say is, if I'm trying to capture,
Ask you a question, maybe it'll come to.
Yeah.
So, what I hear you saying, and it makes a lot of sense. We know that natural networks are not random. We know that there's a certain particular structure to them,
Yes,
and preferential attachment, all that kind of stuff. So it makes sense that it makes a sort of intuitive sense, and that's always dangerous. We learned last week about how dangerous it is to, to trust our intuition. But it seems consistent that since natural networks are not random structures, you could a smart there ought to be some smart way to study them in terms of this, and perhaps different ways to look at it for different things you're looking for. But in general, collecting all the data only makes sense if it's truly a random network, because you don't know what's being smart about that.
Yes, exactly.
And so then the question is, how do you do that for different things, your different characteristics you're looking for? And also, I kind of a side question, which I was going to save to the end, but you can answer it at the end, which is, are there sort of, it still comes down to statistics at some point.
Yes,
what sort of sample size do you need to study to actually make sure that you're studying this in the right way? And that may not be possible to answer at this point, but it seems like in order to get the natural characteristics, characteristics that you can actually study in a meaningful way, you are going to have to, the thing that you apply your algorithms to are going to have to be some sufficient size for that.
Yes. No, what I was looking for was characteristics or traits or patterns. No, not patterns. Characteristics or traits. So there definitely has to be some start somewhere. Okay. What I'm trying to run away is from, like I said, two things. One is knowing what I'm looking for, number one, and two is searching through too much of data for what for what I'm looking for, without really knowing what I'm looking for. So it just becomes too much, and it is a very, very impractical solution, given that big data is actually a fact. It is experienced these in our times. So that's why so one does need a large a sample set of characteristics, traits. I need to have some idea of which layer in the network I'm looking at, what application. There has to be a large sample size for that, and what nodes will be useful in when I'm going through those set of characteristics. Which node will be giving me most let's say optimal response for a given characteristic? That will be found out through node centrality algorithm. So that is where I was getting to. And by adaptive, again, by adaptive I mean that system is in place of having those sort of data. You can even increase those traits, but the whole point comes down to that the nodes will be there, information will be gathered, but you're not focusing on all the information all the time. It can change depending on what kind of attacks or what kind of anomalies you're seeing. Okay, and then I haven't really thought too much about it, but again, intuition sometimes tells you what should be the next step.
Yeah, but we have to be careful.
Which needs to be supported by enough research
Yep.
and results. But you start somewhere, even with your intuition, it's not useful. So yeah, I think I've already answered that. So the approach that I'm proposing is identify a set of central nodes for a specific set of anomaly detection. How am I going to test this? Is by obviously knowing that a given set of characteristics basically means this kind of attack. So maybe at a later time I'll be able to use that this idea. So focus not on attack identification, but on anomaly detection. That's where I've changed my path for efficient and more optimal identification of threats and attacks on a network. Meaning of attack changes with time in application, like already cleared. And identify important nodes where a lot of anomalous activity is detected and monitored just roles. So how am I going to do that? Like I said, I'm going to be using graph theoretic analytics, and node centrality is a very commonly used concept in graph theory. Centrality of nodes is not an individual attribute. So this slide basically explains what centrality does. It's like a comparative comparative quotient, basically. So given a large network, a certain node will hold more importance either in the subgraph or in the larger in the entire graph, depending on what you're looking at. So basically it's all relative to the other node in the graph. And so there are various ways of measuring centrality, and the next few slides will be covering those. I explored all of them to see which one is most suitable for the application that I'm looking at. And degree centrality is basically the number of nodes that are connected to a given vertex. Betweenness is it's the ratio of the shortest path that passes through a node to the shortest path between nodes. So it's basically you're picking up N1, N2 from the whole graph, and then a certain vector that lies between those two nodes will get the value of the shortest path between those two nodes. So this is betweenness, and then closest centrality is the opposite of the shortest distance between vertices. And eigenvector centrality is the measure of influence of a node. there's a relative scoring to all nodes based on the concept that if you are connected to a high scoring node, your score also increases automatically. And even if your connectedness is higher, which means the nodes that you're connected to is high in number, but if the scores of those nodes is lower, the value of the vector the vertex will be lower. So basically, if you're connected to influential people, you automatically become influential. That is the concept which is used in mapping vectors.
Even if a lot of people aren't connected to you, that's one of the counterintuitive things about PageRank is that you can have a if your value is relevance, you can have a typically they talk about in links and out links, and that's the sort of the obvious thing. But you can have a node which is just connected to this influential node, and it's not heavily connected, but yet because it's connected to this influential node, it's highly relevant too.
Correct.
And which is
that's
so.
what eigenvectors do.
So if I could just insert a little suggestion here,
Sure.
when you're every one of these centrality measures has there's a cool illustration of them.
I have that as a note.
You definitely you need to. I mean, you're in fact I'd say the same. The thing about the whole talk is this is all about network stuff. So you've got there's a wonderful illustration for virtually everything you're saying.
That's
So
I have a this is like my.
This could be really sexy in terms of the different.
You're right.
Less words and more cool pictures.
Yeah, I have another version of this where I have those notes that I have to insert graphs at what places and references and all.
Yeah. So I think that's because this is I mean it's good to refresh everybody's memory on each of these things, but you should also just flash a little picture on that.
Yeah.
I would anyway.
Well, thank you.
But
I'm going to.
But none of these is what you want, though, right?
None of these is what I want. So that people don't ask me why didn't you use this one and why didn't you use that one.
No.
Go back to the definition. Did you know?
Yeah.
According to the definition. So information centrality is the closest to the one that I want to the project that I'm pursuing. But like I mentioned here, the shortcoming is that information centrality has not been covered extensively, which could work to my benefit. Is that I can modify it, and so there are two options to it: either continue to go with the name information centrality or come up with a newer name. So we'll see how that goes. Because this hasn't been used, and it was extremely difficult to find a paper which focuses on information centrality. Now, what is information centrality? So information centrality basically means the average of information passing from a node. So again, from focusing on one node, what is the information centrality of that node? One starts to do that by picking up a set of two nodes anywhere in the graph, and if the average of information is given a certain number. That is how it works.
So are we actually using a Shannon definition of information? I mean, this is hand-waving information. This is not.
Again, the problem here is because it hasn't been used extensively.
I just want to make sure because we never use, nobody ever seems to use Shannon, but I thought, oh, she's going to use Shannon, but she's not using Shannon either.
Think about it.
Well, because it seems plausible in the way that you introduced this that perhaps it was. But anyways, continue. I'm sorry to interrupt you.
So basically, the node that it is passing through will give you the information centrality of the nodes, which are the starting and the end point. So basically, it's an average of all that information. The problem with this definition is that it means information that is passive. So this is moving information.
So I still don't. How do you quantify?
It's very, very, very vague. Trust me. So I try to understand this, and I'm going to explain you to the best of what I understood. Information passes from node A to node B. Okay, that information is given a value. You start giving it a value. Okay, from node A to node B, it passes through a vector, a vertex. Sorry, I keep saying vector.
Yeah.
A vertex. Now that vertex will get that value depending on the value of how many nodes are passed on the path.
Okay.
Okay, and it is averaged by the number of nodes it passes.
Okay. So, is it
So I'll tell you.
Yeah. Okay. Good.
Let's pick up a characteristic.
Yeah.
Okay, that we are trying to measure. All right. So each node will have a certain value of that characteristic. Okay, I have a strength. You know, it's like a range between 0 and I have
Yeah.
a strength of 0.6 for a given characteristic. I have a strength of 0.2 for a given characteristic. Okay, for a vertex on a path. Okay, the number of nodes which are passing, which lie on that path, all of them will have a certain value of that characteristic. Okay.
Okay.
So the vertex that I'm trying to calculate information centrality for will be the average of all those
Along that.
along that path.
Okay.
That's how it is calculated.
So this characteristic is
All
just
possible
an
paths
Yeah.
for that vertex. And they exist. Those paths exist. That's why in the
So-
network it has to exist. That path has to
So
exist.
is there a like an example that if you choose, it seems that even what a node is could be very arbitrary. But if could we choose a node as a could a node be like an IP address, or could a node be a like a switch, or and what then would be an example of a
It could be both.
Yeah.
A node could be an IP address,
okay.
or it could be a switch, or it could be both.
Okay,
I
so
don't know that yet.
so I'm trying to assemble in my mind, a sort of a model. If it was an IP address, maybe the characteristic is what characteristic could be. It could be. I guess it's all arbitrary, because it's
Right
sort
now
of
it is.
defined on.
Right now it's
Yeah.
quite abstract because, like I said, it could be used on any of the layers. It could be used on the application layer,
Yeah.
on the TCP IP layer, on the physical layer. It could be used anywhere. So,
Right,
or it
so
could be
it's-
used a sum of all of them.
So it really is dependent upon what a node is even,
Yes.
but what the particular definition is, really depends on what layer you're operating at,
Yeah.
and so it's information centrality in terms of that layer and
Yeah.
what that node is in
Right.
terms of that layer. Yeah, you're really going to have to you're gonna need an example for this.
Okay, I will
Well, I don't know. I mean,
try
I
to,
think because it's so. I think everything else, the other forms of centrality are very. I think they're very intuitive. Regardless of the kind of what you choose, as that they're often talked about and they're sort of intuitive. But
yes.
with this, it's very abstract. I think, and so you're going to need to really pin it down as to.
Yeah.
Just at least for an example, you need to pin down. Or maybe I'm just too thick to see it right now. I don't know.
No,
No, there's-
I told you, I don't want to make it sound like a disclaimer and then, continue to use information centrality. But this is also going to be a byproduct of the work that I'm doing, is really understand what information centrality, or just get out of using this term and come up with another term.
Mhm.
So basically, it could go either way. Yes, so the problem with how it is defined, literally, is that information passes between nodes, but for my purpose, for security purpose, maybe that's not what I need. I need data which resides in a node, so that I can work on the characteristic of that node instead of the channel. So we'll see how that goes. So from the example that I gave you, was the only example that I had, was the average, calculating the average of a given characteristic. and then identifying which one has the largest number of, which has the highest average in a subgraph, and then picking up. So one cannot really say which nodes will be picked up eventually, because again, like I said, centrality is a range. It's not like it's not an absolute number. You can pick up the top 5 central nodes or the top 10 central nodes. It completely depends on how the analysis needs to be done. So, and then explore statistics that can be calculated for a given set of anomalies. Again, statistics, we cannot live without that. What those statistical models need to be like, that is again going to be the next step. So, but for now, it's all about understanding how information centrality will be used, what it means, and coming up with solid examples for people to understand, and for me to also start with some experiments. So I was able to, Zhao Hui gave me a paper, the only paper that we have found on information centrality, and luckily those folks have had a model running, and I was able to
Netlog.
I was able to get that example running. So
Very
I thought
cool.
maybe it would be cool
Very
to
cool.
have it to just show you how this thing works.
I love Netlog.
So, oh, you do?
Oh yeah.
That's interesting.
You ever used it?
Me
Oh,
neither.
that's
I saw
totally.
it the first time.
It's awesome.
You have to tell me more about it.
Oh, yeah.
Netlog Example.
Yeah, because it's got a long history.
Oh, okay.
But it's great for modeling cellular automata and stuff like that. Yeah.
Yeah, so let's say this is a graph of nodes, these colorful nodes, and the path that I'm referring to is either a path, a trail, or a walk, which basically means nodes can be
Can you see okay?
replicated,
Yeah.
edges can be replicated or not replicated, duplicated, sorry. That is what walk, trail, path, geodesics. Geodesics is the shortest path between N1 and N2 without repeating a link or a vertex.
Yeah, so just to be clear, so this is a model that
Yeah.
that you were given, or did you?
I got it running from some. This is not mine. This is another researcher's.
Right.
I'm going to be using it as a test bed and improving it
Okay.
and enhancing it.
Are you not? Wait, hold on for a second. Christina's asking, don't you see it?
Yeah, this is actually another window. Do you see it?
I see it.
You see it? Okay.
I see it. Hold on for a second. Let me see. Patrick sees it. I think it just may have been missing for a second while you were bringing it up. So I wait a second. Oh, I know what it. Oh, I know what it is. Yeah, she's got it. Okay.
Awesome.
Yeah, Christine just doesn't know how to drive Google Hangouts. That's all. Okay, go ahead.
It's not as intuitive as I'd like it to be honest.
Well, no, yeah. What she was doing was when you're in Google Hangouts, you have to select the window that you want to see.
Okay.
And she was selecting, or it defaults to who's ever talking.
Okay.
So,
right.
yeah,
This is
right,
you.
right. So, and I'm driving what the YouTube sees, and I have to keep remembering that. So, go ahead.
All right.
Yeah.
So this is this small graph of various vortices, colorful vortices. I'm just gonna run it, and towards the end of it, we'll see a few nodes which have been selected as a central node. And this uses information centrality definition.
So what's actually happening right now is information propagating through the
Yes.
network. So, okay, so
Information is propagating through various vortices, and towards the end, the ones with the highest average, like 3 or 4, will be selected. That is how basically central nodes show up. Just to give people, an idea how it looks on a graph. It'll take a few seconds.
okay. So are all nodes originating information, or what?
All of them are originating. Information is just passing. from all nodes.
And is it targeted information? Is it, so?
Yeah, this is hard-coded. That pick these two set of nodes instead of just that we need to have
Okay.
a bounded set of nodes.
So,
Yeah, so these 4, 5 red ones are the ones with the highest information centrality. It doesn't give a number or anything, it's very, very basic.
so can you pop over to, you see the code button?
Here?
Yeah.
Okay. So if you say Ginori, Lambertis, Albizi, this is, these represent the name of the nodes.
Yeah.
This is actually a family network of Italian families.
Ah,
It goes back to 1800s. And I think this was done as an experiment by Padgett and Ansel in 1993. Italian Renaissance family network. So they basically used the same network because it was easy to prove it using, a well-established network.
right.
Enough number of experiments have been done on that network. That's why.
So does it explain, can you scroll a little bit further? I just want to see how it's propagate, if it explains how it's propagating the,
Yeah.
so the first part is just setup.
Yeah, this one is
Yeah, that's making the
And the other ones are like, how does information flow? Does it
Right.
take a path? Does it take a trail? And it describes here what a path means, what a trail means. No vertices or edges are repeated in a trail. So I picked up a walk, by the way. Yeah, let's just straight away go to walk. I picked up a walk.
Okay.
This is the way how vertex and edges are selected between set of nodes.
Okay. So just from the looks of it, it's trying to, for a particular number of cycles, it's just finding different ways to route through the network.
Yeah, exactly.
And so by everybody trying to route through everybody else with a given network
Yes.
interconnect,
Yes.
it's going to, when all is said and done, and all the message passing is over, you'll see which nodes.
Had maximum number of
Yeah.
passages.
I see. Right. So if you nuked one of the interconnects, I'm wondering what would happen. Go back and let's see. So what happens? What the different execution?
Okay, so I just showed you for walk.
That was
Let's
yeah.
see what does the trail do.
So these are just this is just a different way
Yeah,
through, a different
way
set of
to-
rules.
Yeah, different rule to propagate information.
You can use this for like simulating bird flocking and all this stuff. It's really cool.
Yeah. I can reduce the number of passes if this feels like too long.
Or you can also speed it up. You just just move the slider to fast. Yeah.
Oh.
Okay, so that's interesting. So the different algorithm gave you a different.
Yes.
So those two are those red ones are the more central, based on just a set of different decisions that are made as the information is routing.
Yeah.
So each cycle through, it's deciding how it's going to get to a particular node.
Yeah. Exactly.
Yeah. And then if okay.
Oh, it's super fast because I get
Right.
fast.
So this is path, okay. And it achieves is it really random, or does it achieve the same result each time?
No, I think it gets the same result.
Yeah.
We'll go back to walking.
I think it does. I think one thing I remember about Netlog is it's really difficult to get it to be truly random. You have to do some
Yeah, exactly.
entropy kind of a thing or something to
Exactly
make it.
the same.
Yeah.
So anyways, yeah, I'm going to be using this as the base network. And to continue with my work, luckily I got an internship at IBM on this project, large-scale analysis of large networks and graphs,
Cool.
where I will be exploring centralities on real networks of Europe, like some few million nodes in Europe. And I will be able to work on real data. Hopefully, I don't know how much access will I have.
You're not going to be able to do that in that logo.
Oh, this thing is going to crash. It's 1,000 nodes, I guess.
So where's that going to be? Are you the internship? Where are you going to be based?
I'm going to Zurich for 3 months.
Wow.
All of summer.
Awesome.
If the internship turns out to be hopeless, at least the place is. But no, I kind of made sure that I chose the right project and the right people. Yes, so the purpose of this project is to facilitate very fast analysis and knowledge, which I think is very crucial for large networks. Even if it is a network of, it's a WAN of cell phones, even then that becomes a very large network. Thousands, pretty much millions of devices in a WAN.
You know, if there was only some way, you know, some entity that was collecting large quantities of metadata about cell phone calls, you could study that.
Yes,
it would be amazing.
absolutely. I'm looking
somebody
for
that does that. I don't know. I think they're based in Virginia.
Okay, flight to Virginia.
You can work for them, but you never be able to talk about it. The NSA.
They won't hire me, I'm pretty sure. Not now.
All their secrets are out anyways. They're not fun to work for anymore. Well, not all their secrets. There's still some there. All right.
Some uninteresting ones.
So is that the?
Yeah, that is pretty much it.
So.
And what else? Yeah.
So yeah. So this is fat. You know. So I think one of the things that.
That was a long presentation for a few seconds.
Well, yeah. It's just so from a. You know, when you as you evolve this, you know, as you evolve this, there's, you know, a couple things. Obviously, as you answer a lot of the questions about what you're testing this idea of information centrality, really getting to the heart of it and playing with the idea, you'll be able to talk more based on that. You know, when things are unknown, it's harder to get to the heart of things. The using Netlog in your experimentation is really interesting. You know, so the evolution of Netlog was actually started by Seymour Papert at MIT, who among many things was created the Logo language, but he was actually sort of a learning theorist, and I can't remember some of his famous books, but Logo was originally intended to be this sort of language for kids to learn. You know, it's and your programming. You saw it. I don't know if you saw in detail, but it's got this notion of a turtle, which is kind of a cursor.
Yes.
And the Logo has gone through different transformations. This particular version, Netlog, is very powerful, and it's used by a lot of legitimate research now for studying cellular automata, that sort of thing. You know, it was, you know, years ago I was doing work at HP Labs, and I was actually simulating testing some hypotheses about a self-organizing archive. Basically, this you know, using almost like flocking techniques to sort of fight arbitrarily through documents into a pot. You know, would there be ways to sort of have agents that were looking for different properties passing over them and sort of generate what we would call a triple store based on that. You know, so sort of like you've got different agents who are all looking for different things. It's sort of like, you know, You look to see what color they are. You look to see if they talk about the weather. Each agent, all that does is this one thing.
Okay.
Imagine ants kind of exploring a thing, but ants, instead of leaving the same pheromone over it, like they had particular colors depending upon the things that they found. And so I actually used it to simulate that sort of thing. But so it's very powerful, but you got to also be careful that the population is of the scale.
Yeah.
That and you got to be very careful about whether your assumptions are valid and what are the and I think this internship that you're talking about, you'll have real data to explore, so you'll learn a lot about the characteristics of the real data and how you can apply that to the other things. In terms of there was one slide in there, a couple from the end, where your reasoning seemed a little bit circular.
Which one was that?
It's the one about just looking for the towards the end about
Great idea.
no towards the end, towards the average number right there.
Yeah, this one.
That one. Yeah, so precisely what given that you're understanding what this information centrality is, what do you actually mean by an anomaly, and how are you identifying the anomaly? Because and by circular I mean that's kind of the point, is detecting this. So kind of figuring out what your models are and test cases,
Right.
because you'll probably still have to have the equivalent of ground truths, examples from reality. So there's a lot of sort of you may have some simple ideas that have a lot of rigorous testing that you'll have to do. So
Yeah.
I think that the real challenge is going to be experimental design that you can demonstrate is for real. Also, I think in terms of defending this, discussing this work, you got to imagine, particularly in a community that the security community. Okay, so there's multiple communities you could be talking. You could talk to the network analysis community, right? It's sort of like the legs of a stool, right? Okay, you got the network analysis community. It's got to hold up to that. And I see that Patrick's got a question. He wants it to be working now. He wants to buy it. Patrick wants it. He's got customer number one. He wants it right now.
For $10.
But so just get back to it. This is interdisciplinary work.
Yes,
okay?
that's true.
And it's got to pass muster in each of those disciplines. So the network science part.
Yeah.
Okay, it's got to pass muster there. The security aspect, it's got to pass muster there, and that's a real challenge, because they, as you know from coming from that community, they're you're really going to have to justify this. On the one hand, they're all for it. Yes, this is a problem. The fundamental problem you're always chasing. We only know how to identify what we've identified, and when we don't, and so how do we? To some extent, you're kind of following a natural systems approach, because our immune systems, and I think
I did read a few medical papers
Yeah.
to get some inspiration, and I did get in some understanding from there, obviously.
Right.
Because that's what I thought is where most of the research, I think that is more advanced, that research, the medical sciences research is more advanced than the network security or the network research.
right.
And that is way more, the results of that research are way more, they're really important, so the accuracy of those results really matters a lot. And
Right.
even without the tools that we have today, people were able to predict so many diseases, or even able to identify um, the existence of those diseases, the spread of those diseases, epidemics and all that, without the tools that we have today. So a lot of inspiration I still get from that. I do read medical journals and papers
So,
because it's very helpful in giving a different perspective, and then understanding at an abstract level, can I use it in my field.
yeah. So definitely trying to identify those patterns. It's always a very, again, it's a very seductive thing. It's like, oh, I'm going to be inspired by human immune systems and figure out a network immune system thing. And there actually have been companies that have tried to convince that they're introducing some sort of network immune system, whatever. And so, well, cool. I think that's it. Did you have any questions?
I think I'm good.
All right.
Okay.
Any more questions from my Klingons out there? No? Unmute. All right. With that, we'll stop the broadcast, and it's a wrap. Have a great one.